All right. So I talked about scoreboarding. It stalled a lot, which is not a good solution. We want to have another solution that tries to minimize stalls as much as possible. And a guy named Tomasulo came up with his algorithm, or his version of out-of-order execution, which solves basically most of the problems, or at least enough of it, to where essentially every processor nowadays uses it. So it first came out for the IBM 360. Y'all probably haven't studied that one, but that was a huge deal when that machine came out, a big mainframe that had a lot of features. So 3 years after the scoreboarding, they wanted high performance without special compilers. So in other words, the hardware is going to try and do some optimizations for you that the compiler would normally do, is basically what they're trying to say. A couple of quick differences. IBM only had 2 register specifiers versus 3 in the CDC. IBM had 4 floating point registers versus 8 in the CDC. Remember, IBM's did have in-memory register operations as well. Smaller number of floating point registers prevent increasing the compiler scheduling operations, and this is what led Tomasulo to try and figure out how to effectively utilize the registers. And this is the big trick. Renaming in hardware. This is the big one. Basically, what this does is, once it reads your instruction, it says I'm going to add register 2 and 3 and put it into 1. Once it reads that, it rewrites your instruction to be I'm reading from register 20 and 52, and I'm going to put that back into register 4, and I'm going to record that register 4 is really register 1, so when this all finally completes, we'll put it back in. All right, so that's what renaming is, and it'll make a little more sense in hardware why that is so advantageous, but that's the big trick to Tomasulo's method, is he said, I'm just going to rename these registers. I'm going to give them a new register name. And if you can rename them, they don't have to be only 0 through 3. It can be 0 through 500 if you wanted to. And those numbers can specify or be meaningful in different ways. And we'll get to that in a moment, why that's so helpful. Why do we study the descendants have flourished? Yes, i7 uses this, Ryzen uses that. The Alpha chip, which was pretty much the, I want to say the paragon of single cycle or single threaded execution. Basically, this was the biggest single core executing unit that they made. Really, all these other guys are just a lot of mini one of these running around. Basically, everything since the late 90s has been using this. Unless you go into a really small embedded chip, yeah, they're pretty much using this. Our phones pretty much use this as well. All right. So, a couple of quick comparisons. Let's see, control and buffers are distributed with the functional units. Think of it as your scoreboard. Instead of having one master scoreboard, you now have a small scoreboard for every section. For like floating point add has its own scoreboard, but we're going to call it a reservation station. So it's reservation station, aka scoreboard. They have one for the add floating point adder, one for the multiply, one for the divide, one for the integer add, one for the integer divide, etc., etc. So they're all gonna. He took the master scoreboard and just distributed it out. The registers, this is what he called naming. They're either replaced directly by their value if the value is available. If it's not available, you're going to be replaced with a pointer, aka a new number, that points to what the value is that may be executing somewhere else in your processor. And this is what he called register renaming. This avoids right after reads because you've renamed it to point to what the information needs to be, and also avoids right after write because again you're pointing to what the information needs to be from somewhere else in the processor. Mm-hmm. You have way more reservation stations than registers, which is fine, so you can do optimizations compilers can't. And I'll give you a good example of this later on, but this should make some sense because the compiler only knows of the registers. It doesn't know how many register stations you have because that's not something that that's something that can change from processor to processor. But between processor and processor, you only have a set number of registers. So the compiler can only assume the set number of registers when producing the code. So results from a floating or a functional unit, from a reservation station is from the registration station, not through registers over a common data bus. So when it's issued to the reservation station, it either has the value or it's going to get its value from another reservation station. Once it's been in a reservation station, it does not go back to the register file. Loads and stores, of course, treated as functional units as well. So it's going to look something, all right, we're almost there. Integer instructions can go past branches, allowing floating point operations beyond basic blocks. This is really nice because you can execute instructions that may be about 4 or 5 iterations down in a loop while you're still executing a previous one. All right, it's going to look something more like this.
Cool.
Cool. Oh, you got this? You're perfect?
Yeah.
What was that?
Yeah.
Yeah? Uh-huh. I don't believe you. All right. Let's look at the FP adder. I think this is going to be the most helpful. Maybe you have about 2 or 3 adders. You have a reservation station. Here is 3, which are 3 different floating point add instructions that are waiting to be executed. Notice that it's down here and not up somewhere else. You have this set for the adders. This one has 2 multiplies that can be waiting for the FP multipliers to work. So this has multiple instructions that can be waiting. And then you would do the same thing with load, and then we got a store as well. But notice that they're all communicating over a common data bus. And we'll show you how this works in a minute. Well, I'll tell you right now, actually. Whenever someone completes, he writes his result to the common data bus, and if some other instruction was waiting on that result to be completed, then it would be written into the reservation station at that time. Spiffy. And naturally, an instruction can only start executing once its 2 values have been received, not if one of them is a pointer to something else. Okay? Sure? All right. Okay, reservation station components. You have the operation, because your floating point may be between add and subtract, so you need to know what that is. The value of the source. Store, but yeah, so these are the 2 values. So if you're doing add, you have your 2 values, then you can just issue the add and you're good to go. You're waiting for the 2 values to be valid. Let's see, reservation station producing source registers. So if you need to write to somewhere else on the flag, you usually flag it here. No ready flags, because it's always ready. Or actually the readiness is dependent on something else. Let's see, store buffers only have QI for result producing result, yeah, because you only need 1, and then just tells you if it's busy or not. Let's see, indicates which functional units will write to each register if one exists. Register result status. Oh, that just tells you if it needs to write to the register file. Okay. So in this one, 3 stages. You can issue it. If the registration station is free, no structural hazard, you issue it. So this is different. Instead of making sure that there's no read after write hazard or write after write hazard, it just goes back and sees, is there a station available to put this in? If there is, you go ahead and you issue it into the station. And if you can read the registers, you do so. If not, you just rename the registers. When both operands are ready to execute, it finally has its data. It goes ahead and executes. If it's not ready, it watches the common data bus for the result to come back. And then when it's finally done, it writes the result, but it always writes it to the common data bus to all waiting units, and then mark that reservation station available. Yes? All right. Normal data bus is data plus destination, right? The bus is always going to have the data as well as where it's going. Oh, so the common data bus will also say where it came from. All right. And it is a broadcast. Well, it's a bus. Okay. It may look a little more like this. This is going to look somewhat familiar, but I think this will help you understand more what's going on. Notice I have 3 adds and 2 multiplies just for this example. All right, so first off, the load is an add. So we're going to go ahead and issue that. The address is 34 plus R2. Is the first load busy? Yep, because now it's doing something. We go ahead and we issue load 2 as well, because we still have we have 3 reservation stations for the load, so we go ahead and put that in. So yeah, unlike the 6600, we can have multiple loads. This is not an advantage over scoreboarding, because scoreboarding you could have multiple loads in flight. This is just the way that Tomasulo's hardware worked. Multiply can also be loaded into the reservation station as well. So notice we're just issuing these one after another right off the bat. We're not stalling at all. This load would complete at 3. Register names are removed, renamed in the stations, multi-issued versus scoreboard. Right, so what it's saying is VK we're getting from register 4, but VJ we're getting from load 2. So in other words, we're waiting for the first operand to come from the reservation station of load 2, is what this is saying. It's being renamed. Y'all see what's going on there? Mm-hmm. It's just telling you where you need to get it from. Mm-hmm. You issue the subtract, because again, add is available. It can get the first one, let's see, MA1, memory of A1, which is F6, which is where the load came from. So it's whatever value that is.
Wait, go through that again, real quick.
Hold on. So we got the multiply, right?
Mm-hmm.
So we're in the subtract.
Mm-hmm.
This is 4. So notice the write back is being written back on the load. The previous load is actually going to finish because you have multiple loads here. The subtract is going to be issued because you do have the reservation station.
Mm-hmm.
You have a subtract. It's the memory of address 1, aka it's just saying what came back from this first load, because notice that the sub has F6. That's all I'm saying with MA1, is that it's the first load. Notice that it's waiting for the result from load 2 up here to come in. Okay, so it's excuse me, load 2 to come in. So these two guys are waiting, and they know that they need to wait for that reservation station to complete. This is just saying, what reservation station are we waiting? Both these guys are waiting for load 2.
So it's waiting for I understand.
Yeah. The big trick here is that this has been distributed to the actual execution unit to do the waiting, and then the communication is going through a bus.
Once it's into the communication bus, those two.
Yeah, once the load completes, which is about ready to happen, yeah, it's going to take this answer and put it up here and down here, because it's through a bus. It's a broadcast. They're both going to see it.
Okay.
Load 2 complete. What's waiting for load 1? So there we go. The second memory address goes in for those two guys. They can start executing. And again, we looked at the divide. We have a reservation station for the divide, so we can go ahead and execute that as well. Okay.
I like this one more.
Yeah.
It's easier to follow.
It is a lot easier to follow. It's just not what you would do first, is the thing about this one. It ends up being a lot more complicated hardware. All right, so we have the multiply here. We issue it. Is he ready to go? You can just read it off the board here.
Yes.
Yeah.
No, Molt 2, sorry. Is Molt 2 ready?
Oh, I read the yes.
Busy.
Yeah, it's
The
waiting on the Molt 1.
Yeah, so he's waiting on Molt 1, this guy up here. You see that? All right. So he can't do anything. Can we issue the ad? Can we issue the ad?
Sure.
Right. Why can we issue the ad?
Because you have empty adders.
Right. We have empty adder slots. So we can go ahead and issue that ad. Can I start executing?
Probably not.
This is a little more complex to follow.
It does start getting complicated.
Yeah, because the ad's gotta wait for the no, it doesn't have to wait for the divide. It has to wait for the subtract and something else, probably. Well, the other thing's loaded, so probably just the subtract.
Yeah, just the subtractor. That's all it needs.
The color coding helps.
It does, doesn't it? Yeah, so it's still M2. We got that already. We're waiting for add 1 to complete. This guy up here. This one's And of course, this guy down here waiting for the molten one. Excuse me. All right. So, excuse me. What's going to happen when the add completes? Or add 1 is going to complete, which is this subtraction.
Subs and right to the common line.
You're going to write to the common bus, which will allow what to start executing?
Add to
Yeah, the add 2. Yep.
Yeah.
the colors.
The colors help. Yeah, the big thing here is versus scoreboard. The scoreboard has to stall when it issues the add. It has to do it. But Tomasulo does not. Okay, hold on. There's another cycle for it to complete. Add 1 completing. What was it waiting for? There you go. It updates add 2. Now add 2 can go. We'll go ahead and take another cycle. It goes to 0. And then that is going to, let's see, writes to F6. Notice that he is going to go ahead and write to F6. In scoreboarding, it would have to stall. Why does this one not have, why can you go ahead and complete the add in this one as opposed to scoreboarding?
You don't have to
Because
worry
that's the
about
value,
war.
right?
Right. The war hazard has been taken care of because
That's the value.
this guy, or yeah, the add, well the add, that's the add, he's writing, I'm sorry, I got confused. I ran F6. Normally, the divide down here, sorry, that divide would need to wait for that, before that was written to start executing. But this divide is already waiting for, it already has the value in his reservation station, and he knows to wait for the multiply. So you don't need to worry about stalling to fix the right after right. This method flat out fixes right after right issues. So you can go ahead and just complete that add. Hey, look, you opened up a reservation station. Scoreboarding would not do that. It would stall. All right, right result of add versus scoreboard, right? It's all right. Cycle 12. All right, 13 knows we're just waiting for the multiply to complete. It completes. Once the multiply completes, what's going to happen?
Multiply 2 can go.
Yeah, multiply 2 can go because he's going to be updated. All right, it takes 40 cycles. We'll just skip a couple cycles, and now we're down to 1. And he is completed. Was it waiting for it? Nothing. So if you were to compare these numbers, the Tomasulo method is faster. It took only 56 cycles as opposed to 62. Most of that time was spent waiting for the divide to complete. If we had even a longer pipeline or a longer set of instructions, which is usually the case, hopefully you can see that this would execute even more instructions in the same amount of time. Ooh, I get a little message. What is the MS representing, MMA1? That is representing the memory. I'm assuming what you're talking about is M, these guys right here. What I use that for, notice the color coding, this guy's black. That instruction up there is black. So I was trying to make this specify that what comes back to F6 is the memory. Remember, we're doing register renaming, so this can't be F6 because by the time it gets to the reservation station, it's actually holding the value of what F6 would have been. So in order to show what that means, I just said it's memory of address 1, pretending that this is address 1. This is memory of address 2. Hey, it's whatever came back from the load. Hopefully that made a little more sense. Hmm? All right.
We invented faster than light travel.
We did. It's great. All right, you can compare the two right here. Big thing. Let's see what. Couple of big things to look at. Notice that final add completes a lot sooner in Tomasulo as opposed to the scoreboarding, and that also means that Tomasulo can keep going down and issuing. Notice this is the big thing. Notice that issue, just one after another. It just kept issuing. Scoreboarding would stall, which of course let other things start executing sooner. All right. So why does it take longer on scoreboarding? Yeah, the structural hazards. The reservations get rid of a lot of structural hazards because it kind of buffers what goes to the executing units. And by doing register renaming, it can forward a lot of the information and avoid the write after write hazards. All right, welcome back. So Tomasulo, you can have pipeline functional units. Scoreboard, well, you can both have multiple units as well. Let's see, this one you had 6 load, 3 store. These slides are just kind of showing you what the difference was between the IBM and CDC. Notice that the IBM had a lot more units inside of it, and it could be pipelined. Window size, aka how many instructions can you look down the pipeline? 14, while this one maybe 5 at most due to how scoreboarding worked. Really, you could only hold, in other words, you could only hold about 5 instructions in flight at once. This one you could get up to about 14 is what it's trying to say if you added up all the reservation stations. No issue on the structural hazards, same here. All that's saying is that if all the reservation stations are busy, it still has to wait, so it still stalls. Scoreboarding is the same way there. There's no change in that. Right after read, it avoids by renaming. Scoreboarding has to stall. Right after write, again, avoided by renaming. Again, scoreboard has to stall. And lastly, it broadcasts the results to the functional units, while this one, it waits for it to be written to the register file. So this one does direct forwarding, while this one just waits for it to go back to the register file. And the control is via multiple reservation stations, aka distributed model versus a central scoreboard. All right. Some drawbacks we got, complexity. Ends up being that the Tomasulo method is a lot more complex to implement because you have a lot of reservation stations that they have to communicate to each other via bus as opposed to just having a master control scoreboard, which led to delays in early processors. Many associative stores at high speed, right? They all got to interact. Here's the biggest thing with Tomasulo, and we're not going to go too much into this, is whenever you see the word bus, you should just think slow. They're basically synonymous. So the problem is what if multiple instructions are completing in the same cycle? It's a bus, so only one can complete at a time. You now need to have some type of arbitration logic inside of it. Yeah, a lot of wiring. Number of functional units that can compete per cycle is always limited to 1. You probably could fix this with other types of topologies. I mean, if you had a full switching network, that would be great, but that would take up a lot of area and a lot of power. But there's ways to alleviate that we have come up with at least. Non-precise interrupts. Remember earlier, if I interrupt the processor in order, 5-stage in order, you can just flush the pipeline and you're good to go. You can just restart where you began. Here, well, instructions ahead of you may have already completed. So you got to figure out how you're going to fix those interrupts. We'll address that later, or possibly not at all, because that's actually kind of a hard thing to do.
I like that solution.
You like the second one. All right. Let's go do another loop example. I'll go pause the video. Maybe I have another question. No. Okay. Hopefully I answered that for you, Bart.